Hello students, welcome back. This side Pushpen Singh Rajawat and I am here to take you to a journey of the periodic classification of elements, which is our second chapter. In your life you came across many elements, just for an example say iron, aluminium, oxygen, hydrogen and many compounds like carbon dioxide, H2O. So these compounds are formed by the combination of elements, and how these elements are arranged and do they have any kind of similarity. So 118 elements are known to mankind, out of which we have arranged the elements on the basis of their properties such that the elements with the similar properties are falling under one another, while the elements with the dissimilar properties are simply separated out. So here we are going to deal, that is the periodic classification of elements in this particular chapter. So for that you must need to know what is the meaning of the element, the classification and the term which is periodic. So let us start with the first term, that is elements. So what are elements? Elements are those pure substances which cannot be subdivided into two or more simpler substances by any physical or chemical means. It simply means that, just for an example, if you are having iron, so iron is what? Iron is an element. If I take a sheet of iron, it is composed of very small particles that are called the atoms. So this iron, you cannot subdivide this particular iron element into its simpler types by any physical or chemical means. It means that this particular iron is an element. Now moving into the classification. So what do you mean by classification? Classification simply means the grouping of substances on the basis of their properties, such that the substances with the similar properties will be collected at some point, while the substances with the dissimilar properties will be separated out. So what happens in the classification of elements? So when we classify elements on the basis of their properties, it shows some trends. It means that the properties of the elements are repeated after certain intervals or after certain elements. So this is here termed as a periodic. So this particular chapter name, that is the periodic classification of elements. So now you know that the elements, when they are arranged in a particular order, they show some periodicity in their properties. So moving into the topic or the contents that we are going to study in this whole chapter, that is number first, we are going to study the early attempts to classify elements. Here what we are going to see, we are going to see as the elements in here, we are going to see as the discovery of new elements takes place, the need for the classification of elements also would have taken place. So what are the attempts? So number one attempts that we are going to see in this lecture number first and lecture number second. Now moving into the another, that is the modern periodic table. So it is due to the early attempts for the classification of elements we have led to the modern periodic table. So we will discuss this modern periodic table in lecture number 3. Now moving into the next part, that is the properties. And what kind of properties? Properties which are showing some kind of trends. So here we are going to see some of the properties and their trends. So here what are the properties that we are going to see? Just like the atomic radius, ionic radius, ionization energy, electron gain enthalpy, electronegativity. So all these kinds of things that we are going to see in this particular topic. So starting with the first lecture, that is the early attempts to classify elements. So what are the contents that we are going to see in this particular lecture? So the number first content is what? That is the need for classifying elements. Moving into the number first classification, which was given by Antoine Levisia. The second, which was given by Johann Wolfgang Dobery-Nernst in the form of the triads. Moving into the next, that is the Lands Law of Octaves. Newland gave the classification of elements in the form of octaves. And last but not the least, that is the Locomotor Curve. So it is one of the important aspects in the determining the periodicity of elements. It is also as important as Mendeleev's classification in the bringing of periodic table. So starting with the first, that is the need for classifying elements. So you can see as the time passes, new elements were discovered or on the verge of their discovery. So to classify each and every element and study their properties, that which element shows what kind of properties, it becomes somewhat difficult. So there comes a need for the classification of elements just to make their study very much easier. So now moving into the very first classification, that is the Antoine Levisia classification. So Antoine Levisia classification was mainly based on their properties. So he classified the elements on the basis of metals and non-metals, and he gave the classification in 1789. But as the time passes, his classification became inadequate. He not only classified the elements on the basis of their properties as metals and non-metals, he also classified them as the elastic fluids and also to the earth category. In the elastic fluids, he placed light, heat, oxygen, hydrogen and nitrogen. You can see here clearly that some of the non-metals were also placed in this particular category apart from the non-metals. While in the non-metals, he placed like hydrochloric acid, hydrofluoric acid and boric acid, which are what? Which are the compounds. And in the earth, he placed some of the compounds. His classification was not as good as it should be. But remember students, he gave the classification at the end of the 18th century, which was a long time ago. Now moving into the next slide, that is the John Dalton and his atomic theory. The John Dalton gave his atomic theory in 1808, in which he told us about that the everything around us is made up of matter, and if we keep on dividing that matter, it is composed of what? It is composed of very small indivisible particles called atoms. So he was the one who coined the word atom. And what did he does? He also gave the symbol of elements that were known at that time. Not only this, he also gave the atomic weights of the elements. So after publishing of the atomic weights by the John Dalton, every other scientist and chemist around the world tried to correlate the properties of the elements with their atomic masses. Remember students that only 30 elements were known at the time of John Dalton. So who are the first to give the classification of elements after the publishing of atomic masses? So the first chemist was Beryllium or Johann Wolfgang Beryllium, a German chemist. So here you can see in 1817, Beryllium or Johann Wolfgang Beryllium, a German chemist, gave the arrangement of elements. So how he gave the arrangement of elements? He simply classified the elements on the basis of their properties and grouped them into a triad. Yes, you are right, that is a group of 3 elements which he termed by the name of triad. Here you can see that he arranged the element with the similar properties in the group of 3 called triads. So just for an example, if element X, Y, Z and A, B, C, these are what? These are the 6 elements, out of which 3 elements are showing some kind of similarity. Just for an example, C, Y and Z. Just for an example, if these elements are showing some kind of similarity, so he placed these elements and forms a triad. But not only he forms a triad, he gave one interesting fact that the atomic mass of the middle element is simply the arithmetic mean of the first and the last element, or the atomic mass of the middle element is just simply the or approximately the atomic mass of the first and the last element. So this was his statement, that is, according to Beryllium, the atomic masses of the central element was merely is used for the approximation, merely the arithmetic mean of the atomic masses of the other 2 elements. So let us check it out, what are the triads that the Beryllium gave to us and how this calculation works. So moving into the triads which were given by Beryllium, that is lithium, sodium and potassium. The symbol for lithium is Li, for sodium it is Na, and for potassium it is K. The second triad which was given by Beryllium is calcium, strontium and barium. The third triad, that is sulfur, selenium and tellurium. The next triad which Beryllium gave and which fits into the calculations or the statement which was given by Beryllium, that is chlorine, bromine and iodine. He also classified some other elements, but they were not obeying his own statement. So we will deal with it later on. So let us check it out how this lithium, sodium and potassium fits into the Doberanner's triad. So moving into the lithium, sodium and potassium. Here you see the atomic mass of lithium is 7 while that of potassium is 39. So how to get the atomic mass of sodium? So how to get the atomic mass of sodium? So here what you have to do, you have to take the arithmetic mean or simply the average of first and the last element. That is, the atomic mass of first element is 7 and the atomic mass of the last element is 39. And if you are taking the average, it means you have to divide it with the help of 2 because there are only 2 numbers. So here you get that is 46 divided by 2, which is equal to 23. So this is what? This is the atomic mass of sodium. So this fits perfectly into the triads. And also remember, all these lithium, sodium and potassium, they have their similar properties. So now moving into the next, that is calcium, strontium and barium. Here you see how the atomic mass of calcium and barium will lead to the atomic mass of strontium. So checking, that is atomic mass of calcium, that is 40 and the atomic mass of barium is 137, and taking their average, it is, that is 7 1 divided by 2, and you get that is 88.5, which is approximately equal to what? Which is approximately equal to 88, or the atomic mass of strontium. So now moving into the next triad, that is chlorine, bromine and iodine. So here checking for this particular triad, the atomic mass of chlorine is 35.5 while that for iodine it is 127, and taking their arithmetic mean or the average, we are getting what? We are getting which is approximately equal to what? Which is approximately equal to the atomic mass of bromine. So Doberanner's gave a fantastic triad in which there is a magic associated with the each triad. Just if you know the atomic masses of the first and the last element, you can easily find out the atomic mass of the middle element or the central element. So now here you see in this particular table, which is the modern periodic table, in this you see that the Doberanner's triad fits perfectly as lithium, sodium, potassium, calcium, strontium, barium and also sulfur, selenium and tellurium, and chlorine, bromine and iodine. So these are the earlier classifications of the Doberanner's in an attempt to classify the elements. So moving into the next, that is the question part. Here the question 1 says A, B, C are the elements of Doberanner's triad. If the atomic mass of A is 9 and that of C is 39, what is the atomic mass of element B? So here what you have been given? You have been given 3 elements A, B, C. These are what? These are the triads of Doberanner's. So here the atomic mass of A is 9 while that of C is 39. And what you have to find? You have to find the atomic mass of element B. And since they are the triads of Doberanner's, so you have to simply do what? You have to take the arithmetic mean of the first and the last element. It will lead you to what? It will lead you to the atomic mass of middle element or the element B. So taking the arithmetic mean of the first and the last, that is 9 plus 39 divided by 2, we are getting 48 by 2, which is 24. So this 24 is what? This 24 is the atomic mass of element B. As simple as that. So moving into another question, that is A, B, C are the elements of Doberanner's triad. If the atomic mass of A is 16 and that of B is 30, what is the atomic mass of element C? These questions were taken from the NTSC examinations. So let us check it out. So statement says that A, B and C are the triads of Doberanner's and the atomic mass of A is 16 while that of B is 30. So what you need to find? You need to find the atomic mass of element C. So here moving just like as we did in the previous questions, taking the average or the arithmetic mean of the first and the last element will lead us to what? Will lead us to the atomic mass of the middle element. So atomic mass of B will be equal to what? That is the arithmetic mean, or simply you can write as atomic mass of element A plus atomic mass of element C divided by 2. So on solving we get what? That is 30 will be equal to what? 16 plus, let assign the atomic mass of element C as X. So we get what? We get 16 plus X equals to 60, and X comes out to be 60 minus 16, which is 44. So the atomic mass of element C here is 44. It is a very simple type of questions, but you need to remember the concepts. So moving into another type, that is the atomic mass of element A, B, C and D are this and this. So writing A, B, C, D. These are the elements, and their atomic masses are what? That is 19, 35.5, C 80, and for D it is 127. So these are what? These are simply elements. Which among these elements forms Dobereiner stride? So for finding the Dobereiner stride, either ABC would have formed the Dobereiner stride or BCD would have formed the Dobereiner stride. So checking for A, B and C, and also for the B, C and D. So in this case, what you have to do? You have to do what we have did in the previous questions. Taking the arithmetic mean of the first and the last, we will lead us to what? We will lead us to the atomic mass of element B. So checking for A and C, that is 19 plus 80 divided by 2. So here we got that 49.5. So this 49.5 and the atomic mass of element B is 35.5. So they are not at all equal, not even approximately equal. So moving into this particular type, that is B, C and D. So taking the arithmetic mean of the atomic masses of B and D. So for B it is 35.5 and for D it is 127 whole divided by 2. So what do we got? Here we got that is 0.5, that is 81.25, which is approximately equal to what? That is the atomic mass of element C. So B, C, D here they are forming the Dobereiner's triad. So now moving into the next, that is the limitations of Dobereiner's classification. You all know that during the time of Dobereiner, many elements were known, more than 30 elements were known at the time of Dobereiner, but he only gave the classification of 12 to 16 elements. So what about the other elements? He did not classify those elements on the basis of their properties, and or those elements could not be fit into the Dobereiner's triad. So his first limitation was it was restricted to only few elements, and the second was that the atomic masses of the three elements of some triads are almost equal. Here you see that is iron, cobalt and nickel. So they are forming what? They are also forming a triad, but checking the atomic masses of the first, the last and also the middle element, the Dobereiner's statement did not fit correctly for this particular triad. So moving into another, Newland's law of octaves. In 1866, English chemist John Newland, he proposed a new system of classifying elements. So his new system of classifying elements was based on the atomic masses. He simply arranged the elements with the lowest atomic masses, that is of the hydrogen, and moved up to the thorium, which was the 56th element known at that time. And what does he got? Let us see. So he tried to correlate the properties of the elements with their atomic masses, and from where he started with the hydrogen and he ended with the 56th element, that is thorium. And how he arranged those? He arranged in the order of increased atomic masses. So what does he got? He got that every eighth element had the properties very similar to that of the first. So he gave the name law of octaves, which was very similar to the musical notes. Here you can see that there are 7 musical notes. So let us check it out. So the first musical note is do, then re, then mi, then fa, then so, la and ti. So T is what? T is the seventh note. Just like this is first, this is second, this is third, fourth, fifth, sixth and seventh. So after 7 what is coming? So after 7 there is a repetition of the first note, that is do. So here instead of placing this 8 I can call it that I am simply using what? I am simply using the first note. So this is what? This is the similarity in the musical scale. That's why the Newland call it as the law of octaves, because when he arranged the elements in the increasing order of their atomic masses, he observed a similar pattern which was very similar to the musical scale. That is, the properties of the elements repeated after every 7th element, or I can say that the properties of every 8th element was very similar to that of the first. So seeing this, he gave the name, that is the law of octaves, due to the similarity in the musical scale. So here you see that is a musical scale which 1, 2, 3, 4, 5, 6 and 7 notes are present. So he started with the hydrogen and placed it at the starting position, and when he moved to the further elements and when he arranged the elements in the order of increasing atomic masses, just like lithium, which is having the atomic mass greater than that of hydrogen, and beryllium, which is having atomic mass greater than that of lithium. So as he arranged the elements just like that, so here he encountered with the fluorine, and as he see that the fluorine is having the properties very similar to that of the hydrogen, so instead of placing it at the 8th position, he placed it under the 1 position. So here you see the fluorine is placed under hydrogen. Also, the properties of sodium are very similar to that of the lithium. So he placed sodium under lithium metal. As in the case, you can see the elements are arranged in this particular fashion. This is just a part of Newland's classification. We have not taken all the elements in this particular table. So moving into the next, that is the limitations of law of octave. Newland and Dobryniers, they gave a fantastic classification of classifying elements, but at their time the elements were also very less and they laid the foundation making of periodic table. So here you see that this law of octaves was found to be applicable only up to calcium, or we can say that this law was applicable only up to lighter elements, that is up to calcium, and this law was not applicable to the higher atomic masses elements. Just in the case you have seen here that up to calcium it works very well, but after the calcium the similarities in the properties is nowhere to be seen. Just for an example, if you say here the iron is placed in the oxygen and with sulfur. So these are what? These are the non-metals, while iron is what? Iron is a metal. Also you can see that the manganese is also placed below nitrogen and phosphorus. So nitrogen and phosphorus are what? They are also non-metal, while the manganese is a metal. So it do not resemble the properties with that of the nitrogen and phosphorus. So this was his limitation, that his law works very well up to calcium, but after calcium his law does not work very well. So moving into another type, that is the position of hydrogen along with fluorine and with chlorine was not justified on the basis of their chemical properties, because hydrogen shows properties very similar to that of lithium and sodium. So he placed the hydrogen over fluorine and not over lithium. So this was also not justified. Second, as I have already told you that he placed some unlike elements under the same slot. Just for an example, you have seen that iron is placed in the slot of oxygen and sulfur, manganese is placed under the slot of nitrogen and phosphorus. And also, just to fit the elements in his table, he simply put 2 elements in a particular slot. As you can see, cobalt and nickel are placed in one particular slot. Also you can see that cobalt and nickel, they are metal while they are placed in between these halogens. So this was his limitations. So now moving into the another type of classification which was also very good at that time, but the Mendeleev published his periodic table just before Lothar Meyer published his curves. So the whole credit of classifying elements periodically goes to the Mendeleev. But Lothar-Meyer curve is also very important. So you can see here that Lothar-Meyer is one of the pioneers in bringing the periodic table, and also he received a Davy Medal in conjunction with the Mendeleev for his work in the classification of elements. So now it's our time to study what is the Lothar-Meyer curve. So he classified the elements on their basis of the physical properties, that is their atomic volume, and he take the relation with their atomic masses. So he simply arranged the elements in the order of increasing atomic masses, keeping in view that is their atomic volume. So he pointed the atomic volume on the graph and he got this particular type of arrangement. So you can see here that this graph looks so much complicated, but it contains lots of information. So what are those information and what are the periodic trends that is coming in here? So let us see. Number first, that is here you see that is lithium, sodium, potassium, rubidium and cesium. So these are what? These are the family of alkali metals, and they occupy which position in these particular curve? They occupy the peak positions in this Lothar-Meyer curve. So these are what? These are alkali metals and they are placed at the peaks. Also you see that the atomic volume of lithium is less as compared to sodium and as compared to potassium. So as we move from lithium to sodium to potassium to rubidium to cesium, the atomic volume or the atomic sizes increases. So this is what? This is also a periodic trend. So moving into another, that is fluorine, chlorine, bromine and iodine. So here you see, if this is what? If this is a mountain, this is the peak, then this would be what? This would be the ascending position, and this would be what? This would be the descending position. So here you see that the fluorine, chlorine, bromine and iodine, they all occupy the ascending positions. So the fluorine, chlorine and bromine and iodine, they are called by the name as halogens, and they are placed at the, or simply they occupy the ascending positions. You can also get an idea that the size of fluorine is smaller as compared to chlorine and so on. So this was also a periodic classification. Now moving into the another, that is beryllium. So here I have, so moving into another, that is beryllium, magnesium, calcium, strontium and barium. So these alkaline earth metals, they are occupying what? They are occupying the descending position of this particular curve. So alkaline earth metals, which are what? Which are beryllium, magnesium, calcium, strontium and barium, they are occupying the descending positions in this curve. So this information we get from the, so this information we are getting from this particular curve. Also you can see here, that is the transition elements which are occupying the feet of this curve. Here you can see the transition elements or the D block elements, they are placed at the bottom of the curve. So this particular curve is so much important for you as it contains so much of information, and also it comes in your examinations. So now what we have seen so much classification. So starting from the first and just revising in a few seconds, that is number first, Antonio Lavoisier's, that is the first classification was Antonio's Lavoisier. He classified the elements on the basis of their properties, that is the metals and the non-metals. The next classification was given by Toby Reiners. He classified the elements based on their properties into triads, that is the group of three, in which the atomic mass of the middle element was simply the arithmetic mean of the first and the last element. Next we have moved to the Lands Law of Octave. Newland, starting from the hydrogen, move up to the thorium, which was the 56th element at his time, and he arranged the elements by simply putting the elements on their increasing atomic masses. And what did he get? The periodicity or the repetition of properties of certain elements. After which we have seen the Lothar-Meyer curve, in which you have seen that the alkali metals were placed at the peak while the halogens occupied the positions at the ascending positions, while the halogens occupied the positions at the ascending part, while the alkaline earth metals occupied the descending positions in this curve. Also, the transition elements or the d block elements, they were placed at the bottom of the curve. So, this was all about the lecture 1. Before moving into this chapter further, why not let's revise the concept of class 9. So, some of the concepts of class 9, that is in the structure of atom, and you all know that the atom is made up of what? Atom is made up of subatomic particles, that are electrons, protons and neutrons. The symbol for electron is E, so this is an electron. The symbol for proton is P, this is proton. And where the electrons, protons and neutrons are present in an atom. So let us see. So the electrons are revolving around the nucleus, while the protons and neutrons are present inside the nucleus. So students, in an atom there are three fundamental subatomic particles, out of which the protons and neutrons resides inside the nucleus, or they simply make the nucleus, while the electrons revolve around the nucleus in their shells, or we can say that the energy levels. So now moving further and see that this particular concepts give us the information about something. So what are these? That are the atomic number, mass number, just like that. So what is atomic number? You all know that in the nucleus protons and neutrons are present. So the atomic number is represented by Z, and the atomic number is equal to the total number of protons that are present inside the nucleus of an atom. So Z is equal to what? Z is equal to the number of protons. While the mass number is what? Mass number is simply the sum of total number of protons and the total number of neutrons that are present inside the nucleus, or you can say that mass number is equal to the total number of nucleons. So it is equal to what? It is equal to total number of protons as well as total number of neutrons. Here you can also see the symbol for neutron is small n, and the symbol for mass number is A, which is equals to number of protons and number of neutrons. So how will you represent an atom? An atom is represented by, let us see, so an atom is represented by the symbol that is X, the symbol that is X. The X represents what? It is a symbol for an atom, while the atomic number is represented by Z, which is written on the left hand side corner of this particular symbol for any element, while the mass number, that is A, it is written either on the left hand side at the top or on the right hand side. Just for an example, if I say about hydrogen, so hydrogen atom can be represented by, that is 1H1. It simply means that the number of protons that are present inside the nucleus of an hydrogen is 1, while the total number of protons plus the total number of neutrons is equals to also 1. From here you can check that number of neutrons are 1 minus number of protons for the hydrogen element. So number of neutrons here becomes 1 minus 1, that is 0. So this particular hydrogen element contains only 1 protons and no neutrons. But what about the electrons? Just remember one thing students, that for an atom, if I talk about the atom, atom is what? Atom is electrically neutral. It simply means that the total charge or the total positive charge is equal to the total negative charge. That means that the number of protons will be equal to the number of electrons, because the charge which is present on the protons and the electrons are equal and opposite. So here checking for the electrons, so electron is equal to number of proton, which is equals to 1. So how can you draw this particular hydrogen atom or this particular hydrogen element? So for drawing this, you need to. So students, if I write here that is 1h1, the information that this particular element gives me that the number of protons is equal to the number of electrons is equals to 1, while the number of neutron is equals to, that is mass number minus number of protons, or the atomic number, that is equals to 1 minus 1 equals to 0. So here in the nucleus only one proton is present, while the number of electrons that are present in the hydrogen atom is only 1. So you need to remember these concepts moving in this chapter, because it is very helpful for you to remember what is atomic number and what are mass number, because from the mass number atomic masses have been calculated. Just for an example, we can also see the another example, say the oxygen 8,16. So how can we represent this particular oxygen atom? We can represent this particular oxygen atom as, first of all, the number of protons, which is equal to the atomic number, are equal to 8, while the mass number, that is A, which is equal to number of protons and number of neutrons, is equals to 16. So from here you get the number of neutrons is equals to 16 minus the number of protons, which is equals to 8. So the number of neutrons are also equal to 8. So how can you draw this particular oxygen atom? So you can draw this. So here you see the nucleus which contains the positive charge, because neutrons are neutral. That's why the whole of the charge which is present inside the nucleus of an atom is due to the protons. So this is the first shell which contains 2 electrons, while this is the second shell which contains that is 6 electrons, and also the shell number, this is the first shell 1, 2 and so on. The name of this particular shell is K, L and so on as we move away from the nucleus. So these are the some of the concepts that you need to remember. Now moving back into the chapter, and let us revise, that is the elements, symbols, atomic number, mass number and the atomic masses up to 20 elements. So here you see for hydrogen element the symbol is H, while the atomic number for hydrogen is 1, and also the atomic mass is 1.008. So this atomic mass is contributed by the total number of isotopes for hydrogen element. Just for an example, hydrogen element contains 3 isotopes and their relative percentage is different, due to which the atomic mass comes here in the decimals. So what is the mass number? This is what, this is the mass number, and since it is a number it cannot be in fraction. So the mass number is equal to total number of nucleons that are present inside the atom. So this is equals to 1 in this case. For helium, its symbol is He. The atomic number for helium is 2. It can be represented as 2He4 because its mass number is 4 and its atomic mass is 4.0026, which can be approximately written as 4. And also in the case of hydrogen, you can also write it as 1. Checking for the lithium, the symbol for lithium is Li. Its atomic number is 3, while its atomic mass is 6.94. You can also write it as the 7. While the mass number, that is the total number of protons and the total number of neutrons inside this lithium, is 7. Here 3 protons are present, so the number of neutrons will be 4. Moving to another, that is the beryllium. Its symbol is Be, and you can write it as Be4 9. So here 9 represents what? 9 represents the mass number, while this in the fraction term it is the atomic mass. So from these particular examples you can see that mass number can never be in a fraction. It is the number, and a number cannot comes in a fraction, that is the number of protons and the number of neutrons, while the atomic mass may come in a fraction. So here you can write it approximately as 9. For boron, that is the symbol is B, you can also write it as B511. Its mass number is 11, while its atomic mass you can write as approximately 11. For carbon, that is C612. So its mass number is what? 12, while its atomic mass you can approximately take it as a 12. For nitrogen, the atomic mass is 14, while the atomic number is 7, and the mass number is also 14, while the atomic number is 7. For oxygen, the atomic number is 8. You can check it here. While the mass number is 16. We have seen it in an example. While you can write this particular atomic mass as an approximate value, which is equal to 16. For fluorine, the symbol for fluorine is F. You can write it as F919. So its mass number is 19 and the atomic mass is in a fraction, so you can take the approximate value, that is equal to 19. So these are some of the elements. Let's complete this table up to the element 20, or we can say that up to the atomic number 20. So for neon, the atomic number is 10 while the mass number is 20, and its atomic mass you can take as an approximate value for 20. For sodium, it is represented as Na, or you can write it as Na1123, or you can also write it as Na1123 like this. So its mass number is 23 and its atomic mass is also approximate values of 23. For magnesium, here you can see the atomic number is 12 and its mass number is 24. So from mass number you get the atomic mass, which is equal to 24. So it is also an approximate value, but the real values are like this. Just for the calculations we are using them. For the aluminum, you take that the atomic number is 13 while the mass number is 27. This is approximately equal to 27. So its atomic mass is what? Its atomic mass is also 27. For silicon, phosphorus, sulfur and chlorine, I am writing here, that is their atomic number is 14, 15, 16 and 17 while their mass number is 28. For phosphorus it's 31, for sulfur it's 32, and while for chlorine its mass number is 35. So the number of protons and neutrons that are present inside the nucleus of chlorine atom is equal to 35. It means what? That is 17 protons are present while 18 neutrons are present inside the nucleus, and its mass, atomic mass is what? Its atomic mass is 35.5. So you need to remember that if we talk about the mass number, it is in a pure number or it is a pure integer, while we talk about the atomic mass, it can be either in a integer value or in a fractional value. Now checking for argon. So argon mass number is 40 while its atomic number is 18. So its atomic mass is also 40. For potassium, the atomic number is 19 and the atomic mass is 39.098, which can be approximately equal and taken as 39, and also its mass number is 39. For calcium, the atomic number is 20 while its mass number is 40 and its atomic mass is 40 point something, which can be taken as a value 40. So these are the some of the examples you have seen in which you came across the atomic number, mass number and atomic masses up to 20 elements. So this you need to remember, because we are reading about what we are reading, that is the periodic classification of elements. And in this particular chapter we are going to see that the Mendeleev's classification, the Moseley's classification, and we are going to do some of the questions which are based on these atomic numbers and their positions in the periodic table. So now moving into, that is the did you know fact. Here you see a person, his name is Alexandre Emile Cancouchois. So this person is a French geologist. He was the first to introduce the periodic table. You might not know that, but now you know that he was the first to produce the periodic classification of elements. And how he produced it in the form of this spiral tube. This is also called as the Teloric Helix. Here you can see that when the elements are arranged in the increasing order of their atomic masses, they are showing some particular kind of pattern. So this was his work, but his work never got to publish because it was more in the form of geological graphs. So now